Hello, and welcome to our presentation on progressive transformers for end-to-end sign language production. My name is Ben Saunders, and I conducted this work in collaboration with Najati Jihenjamgus and Richard Bowden of the University of Surrey. Automatic sign language production is a translation from spoken language sentences to sign language sequences. SLP can therefore be formulated as a neural machine translation problem. Previous SLP work has focused on the production of concatenated, isolated signs. However, to fully encapsulate understandable sign, continuous sign production must be achieved. The production of continuous sign introduces many challenges. Firstly, spoken and sign languages have a non-monotonic relationship due to the different grammar and syntax used. Secondly, there is a significant increase in the amount of time steps between words and frames. Finally, sign language inhabits a continuous space, requiring a differing representation to the discrete space of text, and disabling the use of classic NMT techniques such as end-of-sequence prediction. We propose progressive transformers, the first SLP model to translate from spoken language to continuous signpost sequences. We present two model configurations, firstly translating from spoken language to signpost via gloss intermediary. In the second configuration we go direct, translating end-to-end from spoken language to sign. Our network involves two models, a symbolic transformer and a progressive transformer. Our symbolic transformer architecture is used to translate between the symbolic domains of text and gloss as an intermediary step in our T to G to P setup before post-production. Our progressive transformer architecture translates from a symbolic input to a continuous output representation. We use the progressive transformer model for the production of realistic and understandable sign, either via gloss supervision in the T to G to P setup or direct from text in the T to P configuration. Due to the lack of an easily defined vocabulary, end-of-sequence prediction of a continuous sequence is a challenging task. To overcome this, we introduce a counter-decoding technique that can predict continuous sequences of variable lengths. Counter values from 0 to 1 are predicted alongside the signpost, with a value of 1 indicating end of sequence. Counter-decoding enables the model to track the progress of sequence generation, providing a natural end of sequence prediction. Also, it provides the ability to drive the timing at inference, generating sequences of varying speed and length. We evaluate our model on the Phoenix 14T dataset, a corpus of parallel sign videos and German translations. We build 3D skeleton data by extracting 2D open-pose coordinates and using inverse kinematics to lift them to 3D. We introduce a back translation SLP evaluation using a pre-trained SLT model to translate the produced signs back to spoken language. We liken this to the wide use of inception score for image generation tasks. Classic NMT metrics of blur and rouge can then be computed on the resulting back translation. We first evaluate our symbolic transformer on the text-to-gloss translation task for sign understanding. We achieve a state-of-the-art result of 20.223 blur 4, outperforming that of Stoll et al. This supports our use of the proposed transformer architecture for sign understanding. Our next experiment evaluates the progressive transformer for gloss-to-signpost production. We find that our base model suffers from prediction drift, with erroneous predictions accumulating over time. We experiment with multiple data augmentation techniques that greatly improve model performance. Future prediction requires a prediction of more than just the next frame in the sequence, learning the sequence structure. Just counter takes only the previous counter values as input, as opposed to the full skeleton pose. Gaussian noise applies noise to the input skeleton poses, increasing the variety of data to enforce a more robust model. A mixture of future prediction and Gaussian noise augmentations achieves the best gloss-to-pose performance. The increased performance score from 7.04 to 11.93 blur 4 highlights the importance of this data augmentation. Our final experiment evaluates the text-to-pose task, either via gloss intermediary or direct from text. The text-to-pose configuration performs best, achieving a blur 4 score of 11.82. This is an important finding, as it enables SLP applications in domains where expensive gloss annotation is unavailable. Qualitative examples of unseen data are shown, slowed to emphasize produced signs. The original video is shown on the left, with our produced signpost sequences in the middle and the ground truth sequence on the right. The original German input and an English translation is shown at the top. As can be seen from these examples, our progressive transformer SLP model produces visually pleasing and realistic sign, with a close correspondence to the ground truth video. Body motion is smooth and accurate, whilst hand shapes are meaningful if a little underexpressed. We find that the most difficult production occurs with proper nouns and specific entities due to the lack of grammatical context in examples in the training data. Further qualitative examples of our produced signpost sequences are shown. These examples show that producing continuous sequences can be successfully achieved using a transformer-based architecture. The predicted joint locations for neighbouring frames are closely positioned, and smooth transitions between the signs are produced, highlighting a difference from the discrete generation of spoken language. In this paper, we propose progressive transformers, a novel SLP model to translate from text to continuous signpost sequences. We introduced a counter-decoding technique that enables continuous sequence generation by tracking production progress. We evaluated our model on the Phoenix 14T dataset using a new back-translation evaluation method. We presented multiple data augmentation techniques to greatly improve the performance of SLP models. Finally, we have shown the success of a direct text to post-production, reducing the reliance on expensive gloss annotation. Thank you for listening to our presentation. If you wish to find out more or ask questions, please come along to our scheduled Zoom sessions. Our source code is available from the QR code below.